Hello everyone, I am Sumedha. I am from MSc Chemistry first year. Today I am going to read Organic Chemistry Unit 4, which is Elimination Reactions. These are the organic reaction in which two atoms or groups are removed, eliminated from adjacent carbon atoms of a substrate, leading to formation of a double bond alkene. Journal form RCH2CH2X forms RCH double bond CH2 plus HX. X is leaving group like halide, etc. Types of elimination reaction: E1 unimolecular elimination, E2 bimolecular elimination. Even reaction: the reaction of tertiary butyl bromide with sodium hydroxide is a first order elimination reaction because the rate of reaction depends only the concentration of alkyl halide, called even reaction. CH3C CH3CH3Br plus OH gives to CH3C CH3 double bond CH2 plus Br negative plus OH. An even reaction is a two-step reaction. This is following mechanism agreed with observed first order kinetics. Residue selectivity: when two elimination products can formed, the major product is always the one which is obtained according to the Sadjev rule. The H is removed from the beta carbon bonded to the lowest hydrogen. CH3 CH2 CH2 CH CH3 CH3 plus NaOH gives CH3 CH2 CH2 CH3 double bond OH, which is minor product, plus CH3 CH double bond CH3 CH3, which is major product. E2 elimination reaction. The reaction of ethyl bromide with ethoxide ion is an example of E2 reaction. It is a second order reaction because the rate of reaction depends on concentration of both alkyl halide and base. CH3CH2Br plus C2H5O positive gives CH2 double bond CH2 plus C2H5OH plus Br negative. Rate law tells us that ethyl bromide and ethoxide ion are both involved in transition state of rate determining step of reaction. The following mechanism agree with the observed second order reaction kinetics. Factors affecting E2 elimination reaction: effect of the structure of the substrate. It has been found that branching at alpha and beta carbon increase the rate of E2 reaction because number of substituents increase on carbon atoms of developing double bond, the stability of transition state increasing. Example: branching at a carbon. Strength of base: with increasing basicity of the added base, the rates of E2 reaction have been found to increase. The order of basicity is NH2 negative is greater than C2H5O negative is greater than OH negative. Effect of temperature: as the temperature of reaction increase, rate also increase. Even CV mechanism: this is a third mechanism of beta elimination. This one begins with the rapid loss of a proton to base. Loss of proton lead to a stabilized carbon ion. The carbon ion is then converted to an alkene. Conversion of carbon ion to an alkene. Conversion of carbon ion to an alkene is the rate determining step. This elimination, since it proceeds through the conjugate base of starting material, is known as even CB. They are less common than E2 reaction because of greater instability of carbon ions. Product formation generally take place by Hofmann's rule. Leaving group of substrate is generally poor leaving group. Beta hydrogen should be highly acidic so that the carbon ion formed may take place easily and reaction take place in presence of a strong base. Comparison of E1, E2 and even CB. E1 reaction: this is two-step reactions. Carbocations as reaction intermediate. First order kinetic rate is equal to K substrate. Reactivity order is tertiary is greater than secondary is greater than primary. Complete with SN1. Compete with SN1. This is a common reaction. As the temperature increase, the rate is also increase. E2 reaction. This is one step reaction, no intermediate form in this. This is second order kinetics. Rate is equal to K substrate base. Reactivity order tertiary is greater than secondary is greater than primary. Compete with SN2. These are most common reactions. As the temperature increase, the rate is also increase. Even CB reactions. This is two-step reactions. Carbanions as act as reaction intermediate. These are second order kinetics. Rate is equal to K substrate into base. Reactivity order is tertiary is greater than secondary is greater than primary. They are cry rare. As the temperature increases, the rate is also increase. Orientation of double bond reduce selectivity of elimination reaction. As we know that the elimination reaction generation double bonded compound, also the elimination reaction may be either reduce specific or reduce selectivity. Reduce specific elimination reaction produce only one isomer of an alkene. Reduce selective elimination reaction on other hand produce several different isomers but give one isomer in major quantity than the other. So for determination of reduced selectivity of the elimination reaction, or we can say that for determination of a major product, generally we have to follow two rules. First is Set-Jeff rule, second is Hofmann rule. Set-Jeff rule, it is also called as Yates Set-Jeff rule or Z rule is given as a Gel-Save. It is an empirical rule used to predict the major product of elimination reaction. Stated that stable alkene is formed when the removal of hydrogen from beta carbon has a low number of hydrogen substituents. Hofmann rule. According to this rule, major products are always least substituted alkenes, i.e. major product is formed from a beta carbon has a maximum number of hydrogen product of this case called as Hofmann product. Example of Set-Jeff rule: dehydrogenation of 2-bromobutane. When 2-bromobutane undergoes a dehydrohalogenation reaction, it gives two products, 1-butene and 2-butene. Out of these, 2-butene is the major product since it highly substituted and more stable. Causes of Hofmann elimination reaction: dehydrohalogenation of alkyl halides when a leaving group is very poor, for example alkyl fluoride. Effect of structure of substrate, strength and concentration of base, and effect of leaving group in rate of E2 reaction. Structure of substrate: it has been found that branching at alpha and beta carbon increase the rate of E2 reaction. This is because as the number of substituents increase on carbon atom of developing double bond, the stability of transition state, substrate structure and rate of E2 reaction. Substrate CH3CH2Br percentage yield is 0.9. Rate of 25 degrees Celsius 1.0 into 10 to the power 5. CH3CH3Br percentage yield is 80.3. Rate of 25 degrees Celsius is 2.3 into 10 raised to power 5. This shows that branching at alpha and beta carbon increase the yield as well as rate of E2 reaction. This table shows that tertiary halides are more reactive than secondary alkyl halides, which are more than primary alkyl halides. Tertiary is greater than secondary is greater than primary. Since the transition state of an SN2 reaction involves high steric strain, the alpha and beta branches slow down and SN2 reaction rate while they speed up the E2 reaction rate. Thus, with increased branching at alpha and beta carbons, the E2SN2 ratio increase. It has also been found that electron withdrawing group on beta carbon increase the rate of E2 reaction. This is because the -I group on beta carbon increase the acidity of beta halogen and stabilize the carbanion character of transition state. Nature of the leaving group: in general, better the leaving group, higher is the rate of E2 reaction. Thus, when beta phenyl halides are treated with sodium ethoxide in ethyl alcohol, the rate of E2 reaction increase with the leaving power of halogen atom. Leaving group and rate of chemical reaction. Substrate C2H5CH2CH2Cl rate at 25 degrees Celsius 0.007 into 103 1 raised to power 3 3 6 C6H5CH2CH2Br rate at 25 degrees Celsius is 4.2 into 10 raised to power 3. It has been found that with increased size of halogen atom, E2 and SN2 ratio increase, but to a minimum extent. Strength of base. With increased basicity of added base, the rates of E2 reaction has been found to increase. Order of basicity among OH negative, C2H, O negative, and NH2 is NH2 negative is greater than C2H5, OH negative is greater than OH negative. Rate of E2 reaction on a given substrate with above bases under identical condition also found to be NH2 negative in is greater than O, C2H5 negative is greater than OH negative. Thus, order of basicity is also the order of the rate. When the base is weak but strong nucleophile towards carbon, E2SN2 ratio is low, but in presence of a strong base, E2SN2 ratio increase. The effect of temperature. As the temperature of reaction increase, the rate of reaction also increase. Thus, the E2SN2 ratio will also increase with increase in temperature. For example, E2SN2 ratio of reaction of 2-bromopropane with sodium hydroxide in 62% ethyl alcohol is found to rise from 1.15 to 2.45 as temperature is raised from 45 degrees Celsius to 100 degrees Celsius. The nature of solvent. The yield of product is in E2 reaction increase with decrease in solvent polarity because this favors the formation of transition state of reaction. Thus, the E2SN2 ratio in reaction of 2-bromopropane at 50 degrees Celsius with sodium hydroxide has been found increase as solvent polarity decrease. Solvent is 60% C2H5OH and 40% HOH. E2SN2 ratio is 1.17. 80% C2H5OH and 20% HOH. E2SN2 ratio is 1.44. Effect of structure of substrate, strength of base, nature of leaving group and solvent on rate of even reaction. Structure of substrate. Even reaction take place by formation of carbocation as reaction intermediates. Thus, rate of even reaction depends on stability of carbocation. Since plus I effect hyperconjugation and conjugate effect stabilize carbocation, any structure which forms stable carbocation will be reactive. Steric strain around leaving group also favors the formation of carbocation. Thus, order of reactivity in decreasing order as tertiary is greater than secondary is greater than primary is greater than alkyl halide. Strength of concentration of base. Since even reaction do not usually require any base and the solvent molecule serves the purpose which in themselves behave as base, the strength and concentration of base have nothing to do with rate of even reaction. Nature of leaving group. Reactivity of substrate depends mainly on nature of leaving group. The best leaving group are those which are least basic and more polarizable. Thus, the decreasing order of leaving group reactivity is I negative is greater than Br negative is greater than Cl negative is greater than F negative. Mechanism and orientation of pyrolytic elimination. The elimination reaction which only occur due to high temperature only in absence of other reagents like acid, base, solvent, etc. Pyrolytic elimination literally means an elimination reaction is concentrated plus syn reaction occurs via a cyclic transition state in which the organic substrate due to application of heat. Pyrolytic elimination do not require any additional reagent or solvent to occur and mostly carried out in gaseous phase though can be performed in inert solvents. Organic substance acetate amino oxide. The pyrolytic elimination also called even elimination reaction, internal or intramolecular elimination reaction. In this elimination reaction, two vicinal groups on alkenes framework leaves simultaneously through cyclic transition state to form alkene with a syn elimination, so they are also called as pericyclic syn or thermal syn elimination, cope elimination reaction, pyrolysis reaction of L-tertamine oxides. Main features of mechanism involved in elimination internal reaction. Even reaction follows first order kinetics with rate law where K is rate constant. The symbol Rx represents the molar concentration of substrate. Elimination internal is thermally activated and does not need additional reagents like typical elimination pathways where an acid or base is required or sometimes involved charged intermediates. The elimination made must be syn and the atoms must be coplanar, so 5 or 4 membered transition states. Nevertheless, the coplanarity is not necessary for 6 membered transition state. The rate of reaction is not affected by use of free radical inhibitors. Addition to carbon-carbon multiple bonds. Addition reaction. It is an organic reaction where two or more molecules combine to form a larger one, the adduct. These are limited to chemical compounds that have multiple bonds, such as molecules with carbon-carbon double or triple bond. Molecules containing carbon hetero double bonds like C double bond O groups or C triple bond N groups can also undergo addition as they too have double bond character. There are two main types of polar addition reaction. First is electrophilic addition reaction, second is nucleophilic addition reaction. Free radical addition reaction is non-polar addition reaction. Mechanistic and stereochemical aspects of the addition reaction involving electrophiles. In this type of mechanism, a positive species electrophile approaches the double or triple bond as it is electron rich, and in first step forms a bond by donation of pair of pi electrons to the electrophilic subspecies to form a sigma pair. In second step, intermediate form in first step combines with the species carrying an electron pair. Generally, it is negatively charged. We know that the space below the above the chemical bond is quite rich in electron density due to pi overlap, which makes double bond susceptible to electrophilic attacks. Now, because double bond is a Lewis base nucleophile, it will attract nucleophilic part of attacking reagent toward itself, forming pi complex. This pi complex will get converted into carbocation with real sigma bonds. If attacking electrophile having a lone pair of electron which can be donated to neighboring carbon, a 3-membered cyclic cation will be obtained. This cyclic cation is attacked by nucleophilic part of attacking reagent to give final product. Stereochemistry. It is affected by two primary factors. The electrophile can attach itself to the double bond on the same or different side of nucleophile, for example, syn or anti-addition respectively. In addition to the geometrical profile of a tandem E positive and nucleophilic negative, the stereochemistry of final product is also decided by configuration of addition product, i.e. the orientation with respect to rest of the molecule. In other words, the electrophilic addition at the carbon-carbon multiple bonds can be cis, syn or trans anti and may or may not be stereospecific. Only way for nucleophile to attack is from backward if the intermediate is cyclic cation resulting in a syn addition product. Nucleophilic addition to carbon-carbon multiple bond. It is that addition where an organic compound with an electrophilic multiple bond reacts with an attacking nucleophile in such a way that multiple bond is broken. It involves the group to which atoms are being attached accepts electron pairs. Mechanism. Step 1. The driving force for the addition to the alkenes is the generation of a nucleophile X negative that create a covalent bond with an electron deficient unsaturated system. Carbon double bond carbon with N negative charge on a nucleophile shifted to C bond. Step 2. In second step, the carbanion binds with the electrophilic part of the reagent that is electron deficient to form another covalent bond. Stereochemistry, the nucleophile can attach itself to a double bond on same or different side of electrophiles in or anti-addition respectively. In addition to the geometrical profile of addendum nucleophile and E positive, the stereochemistry of the final product is also decided by the configuration of the addition product, i.e. the orientation with respect to rest of the molecule. The nucleophilic addition at the carbon-carbon multiple bond can be cis, syn or trans, anti or may not be stereospecific. Free radical addition to carbon-carbon multiple bond. The reaction of nucleophilic attack on carbon-carbon multiple bonds. Free radical reaction depend on the reagent having a weak bond, allowing it to homolysis to form radicals. Reagents without such a weak bond would proceed from a different mechanism. Mechanism initiation. A catalytic amount of organic peroxide is needed to abstract the acidic proton from HBr and generate the bromine radical. Propagation. The radical initiated addition to carbon-carbon multiple bonds propagates via the attack of free radicals on substrate. Termination. In this, the radicals initiated addition to the carbon-carbon multiple bonds terminates via attacking of free radical on substrate. Stereochemistry. The addition of HBr to acyclic cis or trans olefins at room temperature result in 20% cis and 80% trans product, indicating that the radical addition of HBr to acyclic olefins is stereoselective but not stereospecific. Free radical addition does not occur with the molecules HCl or HI because both reactions are extremely endothermic and are not chemically favored. Regio and chemoselectivity. Orientation and reactivity. Orientation of addition to carbon-carbon multiple bonds. The structural orientation will not affect the final product if either the reagent or the alkene is symmetrical in nature. If alkene and attacking reagent both are unsymmetrical, two different products can be obtained. In such case, one of the products will be major and other one will be minor. The structural orientation is nothing but the preference that double bond gives during its shift to decide which carbon to bind electrophile and which carbon to the nucleophile. The orientation of electrophilic addition rationalized by two different rules. Markovnikov's rule. It says that the negative part of the addendum will go to that part of unsymmetrical alkenes which has lesser number of hydrogen atom, or the electronegative part binds to the carbon with more alkyl group, whereas the electropositive part binds to carbon with more hydrogens. CH3CH double bond CH2 plus HBr gives CH3CHBr CH3. Second is anti-Markovnikov's rule. It says that the negative part binds to less substituted carbon and hydrogen binds to more substituted carbon. Reactivity of addition to C multiple bonds, carbon-carbon multiple bonds. The double bonds reactivity towards the electrophilic addition increase with electron donating groups and decrease with electron withdrawing group. Order of reactivity. CH3CH double bond CH2 is greater than Cl CH2CH double bond CH2 is greater than Cl2CH double bond CH2 is greater than CCl3CH double bond CH2. This order get reversed if the addition type becomes nucleophilic or with electron withdrawing group. CH3CH double bond CH2 is lesser than Cl CH2CH double bond CH2 is lesser than Cl2CH double bond CH2 is lesser than CCl3CH double bond CH2. Substrates like the foam C double bond Z may be CHO or COR etc. Where the substituent is conjugated with double bond almost always react via nucleophilic addition. Order of activation by substituent Z is given. NO2 is greater than COAR is greater than CHO is greater than COR is greater than SO2AR is greater than CN is greater than CO2R is greater than SOAR is greater than CONH2 is greater than CONHR. Addition to cyclopropane ring. Cyclopropane ring undergoes addition giving rise to open chain products. The attack at cyclopropanes can occur via polar as well as non-polar additions. The electrophile type is most important. The final product of electrophilic addition to substituted cyclopropanes is dictated by Markovnikov's rule. Hydrogenation of double and triple bonds. The double and triple bonds in organic compounds can easily be reduced by heterogeneous catalysis. One of most example of such type of addition to multiple bonds is the process of hydrogenation of alkenes or alkynes. Mechanism involved. The hydrogenation of multiple bonds does not proceed without the addition of a catalyst because final product is thermodynamically favorable but the reactants are kinetically stable. Hydrogenation of aromatic rings. It is not easy to hydrogenate aromatic rings. They need or requires higher pressure and temperature. Raney-Nickel catalyst is used for mass level hydrogenation including temperature and pressure of 150 degrees Celsius and 100 to 200 atm pressure. Hydroboration reaction. It is defined as the addition of a hydrogen boron bond to CN double bonds and CO double bonds and CC double or triple bonds. Hydroboration is discovered by Herbert C. Brown. Mechanism involved. The hydroboration reaction are dictated by anti-Markovnikov's rule, which means that H gets attached to most substituted carbon of multiple bonds. The hydroboration reaction occurs via a four-membered transition state. Michael reaction. It is defined as the addition of a nucleophile like a carbanion to an alpha beta unsaturated carbonyl compound with an electron withdrawing group. It is a type of conjugated addition. This process is one of the most practical approaches for the formation of carbon-carbon bonds, where R and R' on the nucleophile symbolize the electron withdrawing groups such as cyno or acyl, making nearby methylene H enough acidic to give rise to a carbanion when treated with a base. R double dash group is a ketone to make the molecule an enone. Nevertheless, it can also be sulfonyl fluoride or nitro group. Mechanism involved. In first step, the carbanion is formed due to the deprotonation of the substrate, which is stabilized by electron withdrawing groups. It is noted that the Michael addition is primarily dominated by orbital picture rather than the electrostatic interaction. Sharpless asymmetrical epoxidation. It is defined as an enantioso selective chemical reaction where primary and secondary allylic alcohols are converted into epoxy alcohols using tertiary butyl hydroperoxide (TBHP). Chiral diethyl tartrate and titanium tetraisopropoxide as the catalyst. Mechanism involved. The mechanism for asymmetric epoxidation starts with the substitution of isopropoxide ligands in titanium tetraisopropoxide catalyst by the chiral diethyl tartrate, which is followed by further displacement via TBHP in resulting complex. In last, allylic alcohol reagent displaces fourth isopropoxide ligand, although resulting titanium complex is supposed to be a dimer. After that, the olefin part get oxidized by TBHP with phase of attack dictated by the chiral DET, resulting in final product stereoselective epoxy alcohols. Thank you.